Hello everyone, my name is Alexandre. I'm a PhD student from the Federal University of Pernambuco, and today I'll present my work under the supervision of my advisor, Dr. Bernardo Horowitz, on how to build a proxy for reservoir simulation based on deep learning techniques for time series forecasting. This research is the result of our victory in a national competition with the objective of developing a proxy to simulate reservoirs for Petrobras. In order to achieve the objectives of this research, it's necessary to develop a proxy, whose input is a set of time series of the controls of the producing and injecting wells in order to predict with adequate precision the rates of the pressure of the injector wells and the rates of the phases of the producer wells. Recurrent neural networks, RNNs, are known as one of the most efficient models for time series forecasting. For that, we might use long short-term memory cells, which divide the memory, also known as state, into two vectors, a short-term vector H and a long-term vector C, which works like a data conveyor that runs throughout the network. The general idea is that the network learns what to store, what to forget, and what to use along with the input data X by training the forget, the input, and the output gates. On the other hand, convolutional neural networks, CNNs, have been widely used in computer vision and image detection by its feature extraction ability. Then it was also proposed to use CNNs as an alternative architecture for the proxy. They are formed by convolutional layers that process data from the input field through sliding filters, also by pooling layers that compress information, and by dense planes, which are very usual in neural networks. A hybrid convolutional recurrent model was also proposed with the objective that the learning set produces networks with complementary features that provide a better efficiency. In this architecture, the convolution network will be used as an encoder to extract features and compress the information to be used in the recurrent network, which will be used as an decoder. Artificial neural network models are able to learn from input and output data that recognize complex patterns. In this study, the inputs are the bottom hole pressures controls for the producers and for the injectors, and the outputs are the responses of oil and water production and water injection. The responses are generated after the reservoir model simulation process, and the simulator used is the IMAX from the Computer Modeling Group, CMG. In this case study, the dataset used is based on a symmetrical two-phase reservoir model that has two partial faults internally. The cells that model the faults have porosity, transmissibility, and permeability equal to 0. The horizontal permeability of the reservoir is constant and equal to 270 millidarcy. The model has 5 layers, with 33 by 33 cells with 9 vertical wells, 4 producers and 5 injectors. The average pressure of the reservoir is 500 psi. In order to build the dataset, the controls of the producer and injector wells were generated in two ways: non-correlated random controls and correlated random controls, with the correlation being posed in time for the same control. For this last case, two disturbance measures were used for well controls: 10% producers and 15% injectors. The magnitude of the disturbance must be balanced and not be too small or too large, because it can violate the physics of the controls in the reservoir wells and generate abrupt changes in the different flow controls. For both types of controls, 3 datasets were generated, each with 366 samples split as the following: 256 for training dataset, about 70% of our total database, 70 for validation dataset, equivalent to 20% of our database, and 40 samples for testing dataset, about 10% of our database. To predict the water rate of a single injector well, it was noticed that using windows of size equal to the control cycle period produces better results than using all the 30 time steps from the dataset in a row, especially using the non-correlated dataset, where the controls change more abruptly. Although, to predict the production and injection of all wells, it was noticed that using a single partition produces better results than using windows, regardless of their size. Using the correlated dataset produces even better results. Next, it was compared the results obtained by using the three architectures proposed: recurrent neural networks with LSTM cells, CNNs, and the hybrid model, all using a single partition and using all simulation timestamps. The smallest error obtained was using the CNN architecture, using samples with correlated controls and a single partition as illustrated in the previous figures. It also presents the smallest number of trainable parameters. That makes it to require less computational effort during the training process. I'd like to thank all the sponsors of this research, which has enabled it to thrive. Also, thank you for watching. If you have any questions, feel free to reach me out.